So we're in the OpenStax Statistics Chapter 9 Excel workbook, and we're going to talk about hypothesis testing with football players. So you can always access the OpenStax text for free. You can look in the description of the video for the link. And if you want to get a copy of the Excel workbook, go to divideandconquermath.com and go to the OpenStax Statistics section. So for this one, we have that a college football coach records the mean weight that the players can bench press as 275 pounds with a standard deviation of 55 pounds. 3 of the players thought that the mean weight was more than that amount. They asked 30 of their teammates for their estimated maximum lift on the bench press exercise. And so the data is recorded in frequencies here. So we're told to conduct a hypothesis test at a 2.5% level of significance to determine if the bench press mean is more than 275 pounds. So first things first, so we got to talk about the hypotheses. So this is not necessarily something that I write down on my Excel spreadsheets. I usually have this written down like off the side on a notebook, but since I'm doing this all on Excel, it's important to know what are your hypotheses. And then there's a few other things that we have to kind of notice here. So we always want to take a second to just organize our data. So we're going to have typically our mean, our standard deviation, which in this case is going to be sigma. So my question is, why is my standard deviation sigma and not S? So this comes down to how this question has been set up. This is given as like a general fact. So the college football coach knows that the mean is 275 and the standard deviation is 55 pounds. So you would think of this as S. So you would think of this as S if this was like tied to, it's 275 pounds because he only from a data set of like 20 lifts. But this is given as a fact, so we can assume that this is sigma. So right now I have that my mean is 275 and I have that my standard deviation is 55. But what's interesting about this now is I can't tell necessarily what my mean is. So my N is clearly 30 because it says they asked 30 of their teammates for their estimated maximum bench press. But as far as the mean from this set of data, you can't tell what that is. So I always first like to go through and organize all the data, and there's kind of a missing piece here. So we'll have to work on that. The other thing I want to talk about before I get into finding this X is I just want to note with the hypotheses. So the book says that mu is equal to 275. So you might want to just always keep these two signs for your hypotheses different, and that to me is not really a problem. But the reason why mu has been set as 275 is it comes back to this opening statement. The college football coach says the bench press really is 275, and is would mean equals. So that's why it's an equals. But if you wanted to turn this into a less than or equals, I don't think that's like the worst problem. It's just this is more exact for the way that this language is set up. And then notice, so the whole thing about this is the players thought that the mean weight was more than that amount. So clearly that's going to tell us then that we want the alternative to be 275. Okay. So just a note on the hypotheses. So now how do we get to what the mean is of these 30 data points? Well, this is going to require some work. So we have this basically like a frequency chart given to us in a really inconvenient way. So what I'm going to do is I've got a weight of 205, and then that's a frequency of 3. Then we have a weight of 215, and that's also a frequency of 3. Frequency of 3. So I don't have a nice way for you to actually do this. Like this is the way that the data was given to us, so this is what we've got to deal with. Now I will say that I did already fill out this frequency chart, so I kind of did this off on the side here since I knew I would need to do this. So I'm going to just show you what the frequency chart comes out to. And, I always like everything to look nice and neat, so I'm just going to center everything. Okay. So you're going to have to just create your own frequency chart, no way around it. And then we have to think too, how do you find a mean from frequency? Well, to do that, so a mean at the end of the day is you have a numerator and a denominator. We can't just use the average function in this case, because what would I be taking the average of? It wouldn't make sense just to take the average of these weights because these weights have different frequencies. So instead what I'm going to do is I'm going to take the product of each weight times its frequency. Again, I'm going to center that because I like it to all look nice. Okay, so I've taken the product of each one of these things, and now I can go through and find my mean. So my mean is taking the sum of these products divided by the number of entries, and we get the number of entries by just adding up the frequencies. And so I can see here that my x will be 286.16, or we could say 286.2, however you want to round that. Okay, so now I have all my data. So we always have a moment to find the data, but then we have to kind of modify this data so that we can use our distribution of means. And so my mean is always the same, but my standard deviation is always found by taking whatever my standard deviation is from the data divided by the square root of my n. So there's my standard deviation. And then the last thing that we'll do is we will find a test statistic, because when I talk about this, I always like to do this two different ways. So my test statistic, I'm really just finding a z-score. So I'm going to take my mean from the data minus my known mean divided by the standard deviation from my distribution of means. So there's my test statistic. Okay, so let's now talk about two different ways to visualize this. So I'm going to do this entire test just using the p-value method, but I'll do the p-value method two ways. So the first way is I'll use the normal distribution, and the second way is that I'll use the standard normal distribution. It's important that you kind of know how to do both when you're first learning this, because usually when you first learn this, it's kind of like, it feels like a lot of information when you first learn this. So you kind of want to repeat this argument to yourself several times, and eventually I think it starts to make a little bit more sense. So the first thing that I want you to do is I want you to draw, what does this situation look like for the normal distribution versus the standard normal distribution. So draw for yourself two normal distributions, pause here, like show what area we're finding, and then hit play when you're ready. Okay, so I've drawn what each distribution looks like. So if we just wanted to use the normal distribution, this would be centered at our mean of 275. And the x that I found, that 286.2, that would be somewhere over here. If I want to use the standard normal distribution, that's always centered at 0, and then I put where my test statistic falls. So I'm going to get the same answer for both of these. So to find my p-value, what I'm trying to do now is I'm trying to find this little area here. And I know that it's in the right tail. I feel good about that because that also matches the direction in my alternative hypothesis, okay? So I'm going to use the norm.dist function. So I use this x. I use the standard deviation from my distribution of means. Oops, I went a little faster. So I use my mean. And then I use my standard deviation from the distribution of means. And then remember, so the norm.dist function always calculates to the left, so I take 1 minus that. So there's one p-value. And I'm going to compare that to the p-value from my standard normal distribution. So now I'm going to use norm.s.dist. And so in this case, I just use my test statistic, which would be really a z-score. And remember, you're still going to take that 1 minus that. And you see that I get the exact same value for both, which is great. Okay, and so now we need to figure out what am I actually measuring this against. So when the problem doesn't say anything otherwise, so your default p-value to compare is always going to be 5%. So if the problem says nothing else, you just assume 5%. But in this case, it says 2.5% level of significance. So in this case, I am going to compare each of these to 2.5%, which is 0.025. And clearly, this value, no matter which way you slice it, is larger than 0.025. So what does that mean? We do not reject in this case because this value is too large. So remember, the phrase is if the p is low, the null must go. We don't have that in this case, so we do not reject. A final note here is that the OpenStax text does have a slightly different p-value, and that is because OpenStax rounded this 286 to 286.2 and just cut it off there, and I use the exact value. So sometimes if you don't round like OpenStax does, you might be just slightly off with your p-values, and so just important to know how to kind of interpret that. So you can easily kind of troubleshoot that by rewriting in what OpenStax had in. So they had 286.2, and then I get the number that I see in the book. The conclusion is the same either way, so it's okay that it's just slightly off in this case, so just a note on that.